These are your 9-2 video notes on dot product, our second day of working with vectors. If you guys think back to 7.1, just some of the stuff there, we kind of did a lot of visual, sort of operational stuff, finding components, magnitude, working with forces, tensions, vector addition, that's all that kind of stuff for the one. So kind of laid all the groundwork of the basic stuff we can do with vectors. For the next couple days, we're going to get into some of the other things. There would be more of the new stuff and less trig-based stuff that has to do with vectors. And so dot product is one of those concepts. So everything today revolves around dot product. First of all, up top in green, I've got some stuff just to kind of give you guys, it's sort of a comparison. So like when you add two vectors together, vector addition, like wind and plane, for example, you get another vector. When you do an operational thing where you do a multiple or addition again, so a scalar times a vector is another vector. So if I take a vector and say I go v is my vector, then I go 2v, again, I get another vector. Dot product actually produces a scalar, so it produces a number. Now, the dot in the middle here is actually not dot as multiplication, it's dot as dot product. So what dot product really means is the first thing you guys got to wrap your heads around. And so I guess sometimes it's sort of you go through this section, you kind of wonder, like, you do all the work, you're like, great, I did all the work, what is dot product? Well, it's kind of like saying, what is multiplication? It's an operation. So dot product is what you get when you take the components of vectors and you multiply the horizontal components together, you multiply the vertical components together, and you add them, and that number is the dot product. So if someone asks you, what is multiplication? What does it mean? Well, you'd say, well, that's what happens when you multiply 2 times 3, you get 6. That's what multiplication is. So dot product is a vector operation. And then it has its purpose. So we'll get into all that in a minute. And then the day 2 notes takes into the applications of the dot product. There's some other ways we can kind of rationalize it, so we'll do that. We'll try to do that with you guys to wrap your head around dot product a little bit. But I think don't get hung up on trying to define it so much as that it's just an operation. It's a vector operation. So it's new. So like, when you first learned how to add, subtract, multiply, and divide, that was new to you, foreign to you, and you got it. And now you know what it means. Well, dot product is a vector operation. And you'll definitely understand that. It's pretty easy to do. So how you find it is pretty simple. There's actually a couple ways to find it, but this is our most basic way to find it. Given the components of a vector, multiply their components horizontal and vertical and add them together, and you get a number which represents your dot product. Let's try to decipher a little bit of what that number could mean to you guys. So another way to kind of try to rationalize a little bit is sometimes we think of dot product as the angular relationship between vectors. So how far apart are they from each other? Different than us going a vector's angle, which is from horizontal, but comparison of vectors to one another. And so basically, let's just start running through and doing some dot product calculations. Here's a list of vectors. Here they are over here, so you got the visual aspect of it. And when I dot them, again, this is something you can do real simple in your head. So if I do a dot b, I did 4 times 2 is 8, 2 times 4 is 8, 8 plus 8 is 16. Super simple calculation. A dot c, that's negative 4 plus 16. Sorry, a dot c, whoops, I missed that. So that's negative 8 plus 8. I was doing the wrong 2 there. And then a dot d, and so on. And so sometimes we think about it as how they're related by angle. Now, one thing you guys would notice is perpendicular. So dot product is 0 actually does tell you that the vectors are perpendicular. That's also got another name called orthogonal. That's a way to determine if you have perpendicular vectors. And then you might go as dot product is positive. If you do like an A and a B, or you do an A and an E, you notice that they tend to be closer together or less than 90. That dot product is negative. That tends to open them up quite a bit. So if you're looking at an A dot D, so angle between there, that's not necessarily 180. It just may look like kind of like that. But that's sort of another way to think about it. That may help you a little bit the first day, it may not, but doing the dot product is still fairly simple. Another way to calculate it is another formula that we will use to kind of help us derive some and use some other formulas that do stuff for us with vector relationships. And so the magnitude of u times the magnitude of b times the cosine of theta, where theta is the angle between the two vectors. And so, for example, just to show you a dot c, just to kind of prove it, so if we did the magnitudes of the two vectors, which are the same because they have the same components with different signs, in different orientation, but square root of 20 times square root of 20 times the cosine of 90. Well, the cosine of 90 is 0, so it wouldn't really make a difference what these were, but you get a dot product of 0. But anyway, it verifies that. And if we had the exact angles here, which I don't have them in there, but if we had the perfect angles between vectors like a and b, we could go to the dot product and it would give us the same value. So dot product is a vector operation. It has some to do with the relationship between the angular relationship between vectors, and then it also is, again, just basically an operational idea, vector operation, a new one. Okay, let's just do some more work with dot product and talk a little bit again about how it compares just to your basic formula. So doing dot product again, super simple. just multiply your a's together, multiply your b's together, add those two, and you get a number. So remember, dot product is not a vector, it's a number. And then let's do the other two, and then we'll talk about these questions in a second. So remember, our component form, or IJ form, doesn't make a difference which one you're in, still works the same. And then if I actually go ahead and take a look at my first two vectors, which were there, why is it a positive dot product? Is dot product be positive or negative? And this is something also to think about. In this case, because the angle between them is between 0 and 90, the cosine of that angle would be positive. And of course, magnitudes are always positive. So that's the idea of another way to connect up, like sort of try to reason this out a little bit, like why is a dot product what it is? So a positive dot product means that your angle between them must be between 0 and 90. Now, on the other hand, we got a negative dot product. So if we check that one out, the angle between these two vectors, whether I go this way or if I go this way, either way, because you're between 90 and 270, or you're basically bigger than 90 is what it amounts to. So you can connect up the sign on a dot product to the angular relationship. Again, just trying to sort of wrap your head around what dot product is. Now, for us, day one, it's kind of just learn how to do it. So don't get too hung up on trying to define it, but just learn how to do it. And then, of course, we'll apply it as we get to day two. So some of the other things we can do with dot product is just determine, again, if vectors are perpendicular. There's another word for that, orthogonal. I think WebAssign actually uses perpendicular, doesn't use the word orthogonal. But the idea is if you got a dot product of 0, which I showed you a second ago, then yes, they're going to be perpendicular vectors. So let's just do a quick dot product check, and let me show you that. So I can see that's not a 90 degree, right? So again, you can kind of try to connect up the dot product to the angular relationship. Again, why is it negative? Well, that's bigger than 90. So it's another connection to make. Again, trying to sort of somehow put a little bit of a stamp on this. Doing C dot D, you get 0. And if I show you those two, and let me remove those. Whoops, I was going to remove those two. Put those back. But the angle between those two is a right angle. So dot product of 0 means orthogonal. So this is a no, not perpendicular. This is a yes. Okay, and again, anytime you do anything vector, it's always good to have something visual to help try to understand what is going on. Well, a couple other concepts then where dot product is useful for us is to actually find that angle. What is the angle between the two vectors? So we've got a formula for this. It's actually based on you solving this for the cosine of theta. There's a proof for that, but I'm not going to do the proof for you guys. It's like just kind of sort of time consuming. I don't know that it'll be beneficial at this point. But anyway, you take that alternative version, you solve for cosine of theta, and now you got a formula for the angle between. So now we just want to know what is the angle between our vectors, which again can be useful when we're doing applications coming down the road. So what I need to do is a couple of different things, right? I need to know what's a dot product, and I also need to know what's their magnitudes. So magnitude, magnitude, and then 38, the dot product, I just did that in my head. So if I'm doing the calculation here, that's 20 plus 18, that's 38. So I don't know that I got to show you that every time. Once you get used to doing dot product, you guys do it super quick. So I got, again, 20 plus 18, 38. Here's my two magnitudes. Now remember, we're trying to solve for theta. What is the angle between the vectors? So that's an inverse cosine calculation. We'll typically go in degrees like we did day one of vectors, so just stay in degrees. And then you can see that actually matches pretty closely to what you got drawn there. So find the angle between vectors, which uses a dot product to help you do that. And then the last thing is the component of one vector along another. Again, this has a good application. Today it's more or less just learn how to do it. So the component of u along v is another way of talking about how much of u's magnitude is in the direction of v. So when we start applying forces and doing applications, this will become important. This will be day two. But we want to figure out, especially if it's weight. Now today we're not going to do weight, we're going to do length. But if it was a weight, and we're having an object that's on an incline, which is where we're going to head to, because so far in 9.1, we did things that were basically on a horizontal as far as like moving an object, right? And applying a force to something. So to get to that point, we need to be able to understand component of u along v. So how much of its length is in the direction of. And so then we can say how much of its force is applied in the direction of. And that's where we're headed with day two. But today it's, again, just learn how to do it. So we got to start with that. So let's go through a series of just kind of quick proof, or I should say like a quick just sort of series of substitutions to show you how the formula comes about. So if we use the cosine of, now, what I'm calling a, by the way, is this right here. That little bit of it right there. So we're going to call that a, which is the horizontal component of the u vector. So it would be cosine is a over magnitude. Then we solve for a, and we go back to our alternative formula for finding dot product, and then we solve for the u cosine of theta, which actually is a. So in other words, we're even though I don't have it sort of built in here at the moment, we're solving for a by solving for u cosine of theta. There's your a. And this is actually the formula for the component of u along v. Now, again, what it is a portion of the u's magnitude applied in the direction of another vector. Again, that has a good application, which is in day 2 of our notes. Today, it's just learn how to do it. So again, it's kind of one of those days where you just sort of learn how to use the stuff. But the formula is pretty easy. You can kind of think of it like this. Imagine that the sun was up here, directly, like high noon, directly above, and the sun casts a shadow. Hits the u vector and casts a shadow. The shadow is the component. So it's basically what is its length? How much of u's length is applied in the direction? So it's a kind of a magnitude idea, a number like magnitude. So think of it as what is the shadow? The distance of the shadow. And then what's the shadow as a vector is another concept that's coming up again in day 2. Now I'll try to show you guys with some visual stuff so we can try to apply it all. But here's 2 vectors. Let's find the component of one along the other. So again, imagine the sun is hitting the u vector and it casts a shadow perpendicular to the v vector, which is the blue one. Sun hits, casts a shadow. How much of u's distance, its length I should say, or magnitude, would be applied in the direction of v? Now, with the shadow casting idea, actually it would be longer than that. A little bit longer than v. So let's go ahead and check out a couple things. What is the dot product first of all? So dot product is 60. Again, we're just using our basic formula, multiply the a's, multiply the b's, add them together. What is the magnitude of v? Because we're going to need that for the formula. So do the magnitude of the v vector. And then fill in our actual formula. So the idea is, in terms of this vector, 8.9 or about 9 of its horizontal, I should say, that portion of the u vector is applied in the direction of the v vector. So again, think of it as like how much of u's horizontal component is applied in the direction of v. And that's basically going to be your component of u along v. All right, that's it for day 1 notes for 9.2.